Suppose that this piston is actually modeled by a cosecant function. Graph on the interval from 0 to 1 seconds. So obviously this is kind of unrealistic, but we do want to practice working with some of those other graphs. And really what I'm asking here is to just pretend it's not sine and change it to cosecant. So we're going to have 2.5 times cosecant of 6 pi times t, and then adding 2.5. So that is our new function. And we are going to attempt to graph this. So this looks like a good opportunity to me to use transformations as kind of a trick to do this. So first things first, we know that cosecant is just 1 over sine. So let's start with the sine graph. And let's take out that amplitude and the vertical shift. Let's make it as simple as we can and do sine of 6 pi times t. So how do we graph that? Well, first of all, we have to scale our x-axis. And the way that I want to do that is by thinking about the period of this function and the interval that we're given. So the period is 1/3. And we're graphing from 0 to 1 seconds. So we want to think about how many full cycles are we going to have in that interval. And so we would just multiply by 3, get 3 over 3, which is 1. So we're going to have 3 cycles. And then what I like to do is kind of make a little mock version of a sine graph to think about how many points of interest we have. So how many points do we want to graph on here, if that makes sense? So the sine function starts in the soil, if you remember that saying. So it starts here, and then we're going to go like this. So that's 1, 2, 3. Very uneven, but you know. And then we're going to see, basically I'm counting those intervals between where it goes from positive to negative, because those are important points. So we want to know this point, this point, this point, this point, this point, and this point. So how many of them are there? We have 1, 2, 3, 4, 5, 6. So I call these 6 points of interest. And that's going to help us kind of scale our axis. So we can do 1 divided by 6, which means we're going to get 1/6 for our step. So that's just kind of like how much we're adding each time as we go along the axis. So let's go ahead and put 6 points on here. So not counting 0. 1, 2, 3, 4, 5. And we'll do 6 at the end. And then count up by 1/6. So do red. So this is going to be 1/6. Then we have 1/3, 1/2, 2/3, 5, 6, and 1. Perfect. And the next thing we want to do is label our y-axis, which we just do with amplitude. So as of right now, it has an amplitude of 1. So 1 and -1. And the midline 0, so it's just the x-axis. Okay, and so we're going to do this in blue. It might be this color. Do this best I can. Oh gosh, not good. All right, there we go. Oh my god. All right, 3rd time's the charm. I feel like this is really illuminating how unequal my intervals are. It's okay. All right, so this is our sine of 6 pi times t, and we can check to see that we have 3 cycles. So you can kind of like sort of hover your pencil over the paper. So 1, 2, and 3. All right, so that first graph is done. And now let's go ahead and change it into a cosecant function. And we'll do that with green. So number 2 is going to be cosecant of cosecant of 6 pi times t. And so remember that cosecant is just 1 over sine. So it's just the same as 1 over sine of 6 pi times t. And so that just means we're going to do 1 over every point. But we really want to pay attention to the points where our sine function equals 0, because we can't have 1 over 0. 1 over 0 is bad. So the sine of 6 pi times t cannot equal 0, which means we're going to have asymptotes at all our points of interest. I know it's kind of a weird phrase, but I don't know what else to call it. So I'm going to go ahead and draw some asymptotes in here. Okay. And then we got to fill in some points. So something important to note is that when sine is equal to 1, like it is at the amplitude, you get 1 over 1, which is just 1. If sine is -1, that's just 1 over -1, which is -1. So we know we have points at all the peaks for our cosecant function. Cosecant. And then let's think about just what it's doing in between those asymptotes. And we're actually going to go more in depth on that later, so I'm just going to go ahead and tell you that the graphs kind of point up. They point away from the peak. So here's that first one, and then we'll do it for the second one. So you're just kind of reaching up from the peak, and you're approaching those asymptotes, but never touching them, because that's the whole point of having an asymptote, is that there is not a value there. Okay, and then we just got to do one more thing. So I'm going to go ahead and actually do all of this combined. So we're going to put the 2.5 out front and then add the 2.5 at the end. All right, so let's kind of think about this. First, let's focus on the first part here. So the 2.5, we know it's going to make it a little bit skinnier, because that's just what the multipliers tend to do when they're greater than 1. But we should also note that everywhere where we have those peaks, which are important points, now we're multiplying those 1s by 2.5. So that's going to change the amplitude. So now our curves are way up here. And then I'm totally running out of space. So I'm just going to tell you what you would do for the vertical shift. So the vertical shift is pretty similar. You're just going to shift everything up by 2.5. So basically these guys at the bottom, let me just do it in purple. are going to end up on the x-axis. And then the guys at the top here are going to go even farther up at an amplitude of 5. Well, technically not an amplitude, but at a y value of 5 is what I mean. Okay, and that covers it.